Dear friends, today in this session we are going to learn about the determination of moment of inertia and least radius of gyration for T sections, channel section that is C section and Z sections. So before that to going into the session, let you revise that P are determined already for the moment of inertias and least radius of gyration for I sections and angle sections that is L section and T section using parallel axis theorem. We are little bit explained in the previous session about the T section, how to use the parallel axis theorem for the same to solve. So before going into the complete depth of that Z and channel section, let again we use the application of the parallel axis theorem in the a simple basic figure to get the repag of the parallel axis theorem. In this particular question, they are asking about the moment of inertia for rectangle section having the dimension of width b and height h about its base. When they are asking about the moment of inertia about its base, we need to draw the axis about the base. For that, if this is a rectangle, the centroidal x-axis will be somewhere between h by 2. This is the centroidal x-axis, where the formula we know that bh cube by 12 is the moment of inertia. But what they are asked about, find the moment of inertia about its base. So the base is here. This will be the base. So for the base, we need to draw an axis about the base. So this would be the base axis. So base axis will be denominated as a BB axis for our convenience, or you can say that it will be a axis also, you can say, just for get the same similarity I am taking it as a BB axis. And for the centroidal x-axis, it will be x and x. By observing, it is understood that the both the axes are parallel. The x-axis is parallel to BB. Hence, you can employ the parallel axis theorem to find the moment of inertia about the base axis. And the distance from this point is your distance d. This is the distance d. That it is obviously it is a centroidal distance, that is h by 2. So this distance is h by 2. So we already know that ixx ixx is equal to b h cube divided by 12. So that we are already known that ixx is equal to bh cube by 12. So in that case, they are asking about the IBB, IBB. So for that, IBB is equal to simply IX plus A B square. So this Ix is equal to BH cube by 12 and area is equal to BH. Area is BH and small d is already equal to H by 2. Then substitute all these values and you will get the moment of inertia about the base IBB. Let's do the same thing. So these are the axes are parallel to the each other. Therefore Ixx is equal to BH cube by 12. Then employ the parallel axis theorem to solve the moment of inertia about the base axis, that is BB. Therefore Ixx plus AD square. The area of rectangle is A is equal to BH. The distance between both the axes is H by 2, that is equal to D. And then substitute the values in the equation IBB. You get the parallel axis theorem equation. Therefore BH cube by 12 into area into D square. Then after solving this one, you will get IBB is equal to BH by 3. So it is observed that IBB is greater than, let us say, it is important resolution that IBB, let us say, IBB is greater than IX, is greater than IX, because if the axis is far away from the original centroidal axis, then the moment of inertia will be increases. This is asked in several times in the ESET, hence you should remember that if the distance d is increases, then the moment of inertia is obviously increases. So the lowest moment of inertia is about the centroidal axis, and the highest moment of inertia will be depends upon the how far parallel axis you are taking the from the centroidal axis. For the solving the same using the parallel axis theorem for the unsymmetrical figures of the standard sections, let us say I section, L section, C section, Z section. For these angular sections also, for these all, we need to have certain procedure to practice which gives the accurate results. So this is the procedure how to solve the moment of inertia for the unsymmetrical figures. Draw the sketch of the figure with the given dimension and inspect for the symmetry axis if any. So as per the given values, draw the figure and look for is there any symmetry axis are available. Then notice all those things and place your object into the first coordinate so that every area is turns into positive. Every dimension is turns into the positive. Let's take the centroid and determine using the analytical method and locate the centroid. Then note down the individual centroid of the parts of the figure. Then observe the distances from the whole figure to the whole figure centroid to the individual centroids in the x and y direction. If all the centroids of the x are equal to the original centroid of the whole figure, then there is no use of parallax theorem. If the x bar is not equal to x1, not equal to x2, not equal to x3 like that of the number of parts, then you need to employ the parallax theorem. Similarly, in the case of y bar also, if y bar is not equal to y1 and y2 and y3 like that, then you need to employ the parallax theorem. So after individual parts are ascertained and employed the parallax procedure, then summarize all the values to get the moment of inertia of the unsymmetrical figure. Let's try to understood how it will be. Suggest the procedure how to determine the moment of inertia of T section with the following data. The top flange is given B by Tf and web is Tw by h. In this case, the top flange is B means the width of the top flange is B and thickness is Tf. And similarly, the web is already given a width of Tw and height beneath the flange is h, or below the flange is h. Then identify the overall dimension capital H, that is h plus Tf, small h plus Tf, and similarly small b. Let us, why we are calculating these capital H and small b, we want to examine that is the hollow rectangle method of principle is applicable or not to find the centroidal axis. For that, draw the figure like this. You observe here, this is the hollow portion and this is the hollow portion. There are two hollow portions. Let us say each hollow portion is the width of b by 2 and height is small h. Okay? So if I made these are the filling, then it will looks like a complete rectangle. If I make a fill like this, this will be a complete rectangle. So in this complete rectangle, if I deduct these two rectangles, then it will become a hollow rectangle like this, or it will come as a T section. But what I observed that in from this figure, that the x-axis axis, which is a centroidal, is unsymmetrical about the hollow portions. This is unsymmetrical about the hollow portions. About x-axis axis. So when we find that these are unsymmetrical distances, you can see that at this figure, the distances from this point to this point is not equal to these below distances. Hence, it is unsymmetrical about the x-axis. Hence, this cannot be used. This method is cannot be used. Therefore, not useful for the T section. So, hence adopt the parallel axis theorem to solve the Ixx to get the centroidal equations. Hence, employ the parallel axis theorem for the Ixx determination. So, we required y1, y2 and y bar to solve the Ixx. Whereas for the Iyy case, let us see that the two are, this is a symmetrical axis, hence flange and web both are having the symmetry on the both the sides. Hence, we doesn't need to calculate the parallel axis methodology. Simply, we can use the standard formulas like b cube h by 12 to identify the Iyy for the both the cases of the flange and web. Hence, this would be the value of Iyy is Iyc 1 plus Iyc 2. So 1 and 2, these are the two portions. Here IYC can be equal to IYC can be equal to B cube H by 12. So this could be B cube and this one will be the IYC. So this is the procedure for the IYC. If let us say if I say that this is the 1, so you simply substitute this is the 1 1. If it is the 2, for simply substitute these are the 2 2. Then summation you will get the total figure IYY. So this is the simple calculation procedure for the symmetrical axis of about IYY. So with this prior knowledge, let us to find the moment of inertia and least radius of gyration for T sections and channel sections and Z sections. Let us do some of the problem for the same. In this particular question, they are asking to determine the least radius of gyration of T section with the following data. ISHT 1200 having a width of 1500 mm flange and flange thickness is 200 mm, web thickness is 300 mm and height of the web is 1000. Now this 1200 is nothing but this 1000 plus this 200 because the T section is represented with its height. Therefore 1000 plus 200 then it is 1200. With this dimension draw the figure and place entire into the first coordinate to determine the centroid and inspect the symmetrical axis. This 1500 is the top flange, hence for this portion 1 is the first portion, so this would be the 1500 and this is the 200 and the width from this point to this point it is 300 and this height from this point to up to this point the height is 1000. So knowing these dimensions and this is the web is the second part. So after dividing the given structure into the parts, let us find the centroid by inspecting the symmetrical axis. By observation you can say that it is not symmetry about the x-axis axis, it is not symmetry, whereas it is symmetry about the y axis, it is symmetry about the y axis, hence this is the symmetry. So whenever you got the symmetry you can easily identify the that corresponding symmetry value, that is x bar here is equal to 1500 divided by 2, 100 divided by 2 that is equal to 750. So x bar can be found out, whereas for the y bar from this point to this point this is the y bar. Y bar cannot be found out by a simple equation, we need to use the analytical method. To find the y bar use the analytical method. So we will see the same thing by placing the all the values. Let us find the x bar and y bar. So as we discussed in few seconds back, so the value is LD by 2, that is 1500 by 2 750 mm. Therefore this is the 750 mm. Then for whereas the y bar has to be calculated by using the analytical method. So y bar is equal to cy by a. So cy by a can be obtained from ay, where the top flange and web are the two parts, and so this is the one and this is the two. Let us take the areas, note it down, and y bar from the bottommost point, from this point we are calculating. For the top flange it should be added, and this is the y1 line. From this point to this point is the y1 line. Therefore we need to add 1000 and 200 by 2. Therefore you got 200 by 2 is the 1100. Similarly, for the web, here it will be at a distance of, for the web portion it will be somewhere from here. So we required, this is the y2. Therefore y2 is equal to 1000 by 2, 500. Then multiply area into y, you will get the ay as a cy. Then add these ays, you will get the cy value. Cy divided by area, you will get the y bar, that is 800 mm. Then mention from this point to this point it is 800 mm. Now it is observed that to determine the Ixx, we are concluded that y bar is not equal to y1 and not equal to y2, because y1 is 1100, y2 is 500 and y bar is 800. Hence all are at different places. So that we are already seen that in that figure. If you please remember, this is the structure like this, and y1 will be somewhere here, y1 line is somewhere here, y2 line is somewhere here, whereas your y bar is somewhere here, your y bar is somewhere here. So all are not equal, hence we need to use the parallel axis. Hence we need to calculate these distances d2 and d1. From this point it is the d1, whereas from this point it is the d2. Calculate those d1 and d2. So d1 is equal to 1100 minus 800, 1100 minus 800, so it would be 300. It is 300. And whereas for the d2 also, if you see that d2 is 500 minus 800, therefore it is also 300. It is also 300. So d1 is equal to 300 and d2 is equal to 300 from these values. Because in the parallel axis we require the distance of the given axis to the centroidal axis is to be squared and multiplied with the area is to be added to the basic centroidal moment of inertia. The same has been denoted in the figure like this. So it is clearly shown that this is the y bar is 800 and individual axis of the first portion, this is the first portion distance. Now the difference between these two is obtained from the y1 minus y bar, so you got the 300. And similarly for the second portion, this is the second portion y bar y2, then the difference between y bar and y2 is 800 minus 500 is the same 300. So use those values in the parallel axis method and frame a table Ixc, area and t square. For this particular Ixc, we need to understood that this will Ixc, the axis will go through from this point hence h will get the cube. Therefore VH cube by 12 has been taken as the XX values, right? And top length and web like that, the same formula holds good for the both. So there are individual axes of the xx and xx. So this is the first one, this is the second one. So for the first one also bh cube by 12 and second one also bh cube by 12, and corresponding values have been used for the both the bh cubes by 12. Then substitute, you will get the answers and get the d square and multiply with the area and add with the AIXE. Then the value of the summarized values will give you the IXX value, 8 into 10 to the power of 10 mm to the power of 4. Now for the y bar case, it is observed that the x bar is equal to x1, that is equal to x2. Hence Iyy is equal to Iyc1 plus Iyc2. Therefore simply we are getting adding the normal centroidal moment of inertia, then it will give 5.8 10 to the power of 10 mm to the power of 4. After finding the Ixx and Iyy, in the problem they are asked about the find the least radius of gyration. So we need to apply the least radius of gyration. R is equal to square root of I by A. So for individual cases, we need to find the radius of gyration of Ixx and Iyy. So the formula for the Rxx and Ryy will be the same. Just replace the Ixx and Iyy in the place of I. Substitute the Ixx and the area to get the Rxx value, and substitute the values of Iyy and area to get the Ryy value. The least radius of gyration among the Rx's and Ryy by observation, it is Ryy only. So the same thing has been mentioned as R minimum. So this is the procedure we are following. Then for the channel section also, they are asking to suggest the procedure how to determine the moment of inertia of C section with the following data. Remember, we are taking a both the flanges are same, the top flange and bottom flange are having the same dimension. Please note, top flange dimension is equal to bottom flange dimension. So in that case, whatever the procedure now we are discussing, that will be hold good. If this is not the case, then we need to apply the parallel axis theorem for both the centroid xxx and both the centroid yy. So why we are taking equal? If we take the equal, the hollow rectangle method will be give the within less time you will get the Ixx value. That is the advantage by taking the same dimension of the top flange and bottom flange. Let me see how it will be. Now it is symmetrical xx about the centroidal xx axis. So the same procedure, draw the sketch and put the total figure into the first quadrant, then inspect the symmetrical axis. The width of the top flange is B and the thickness of the flange will be the TF. The same dimensions are holds good for the bottom also, bottom flange. This is also B and this is also TF, where the thickness of the web is TW and height of the web in between the flange is small h. Therefore, the capital H is equal to small h plus 2 times of the TF. Now inspect the centroidal axis. If you see that, this would be the centroidal axis. So by observing, it is very distinct that the both half portions are symmetric. Hence, y bar can be simply noted that h by 2, capital H by 2. So due to symmetry, this would be the capital H by 2. Whereas for the symmetry inspection about the x-axis axis, let us inspect the symmetry. So here it is not the similar portions, hence this case is not holds good. So for that case we need to use the analytical method or parallel axis theorem method. Now, now let us move to the hollow rectangle method, checking whether it is possible or not. For IXX case, draw the hollow rectangles so that it can be easily understood. Now I am taking the portion as hollow. This is the portion which is similar to this one. So the entire section, if I minus this portion, that will be converted into the hollow rectangle portion. So this TW can be by 2. So this distance is TW by 2. So this thickness is TW by 2. So I made the same thing as a hollow rectangle, and I see that the x-axis axis is symmetry about the hollow portion to be omitted and about the whole section also. That means a solid rectangle. Hence, the hollow rectangle method will holds good. Therefore, the centroidal x-axis axis can be obtained by the bh cube by 12 minus small bh cube. Without calculating any distances and d's, you can calculate the moment of inertia over the x-axis axis. Whereas for the IYY, if I inspect this IYY, it is not symmetry over the both the axes, hence I need to apply the parallel axis theorem. Therefore, centroidal YY axis is to be obtained by the parallel axis theorem, because each part having its own x bar distances and each bar will have their own x bar distance. Let us understood this one. If this is the channel section of the flange, its flange has the and its centroidal axis about the y axis here. Whereas for the web, if this is the web, its centroidal axis will be with respect to x. This will be somewhere here. That means the both the axes are not coinciding, they are parallel to each other. So hence we need to employ the parallel axis theorem to find the IYY for the channel section. With that prior knowledge, let's to solve this problem. Determine the moment of inertia about z axis of C section with the following data. The top length and bottom length 500 by 20, web is 10 by 600. With the symmetrical C section about the x axis, this is possible when the top and bottom are equal. The top and bottom flanges are equal, then this symmetrical x axis is possible. Hence calculate the capital H and small b. That small b will be 490 because 500 small b is equal to 500 minus 10, that is the thickness of the web, that would be 490, and capital H is equal to 20 is the thickness of the flange, and into 2 there are 2 flanges, plus 600 is the web height, therefore 640. So this is the values we are obtained for the B and capital H. Then find the x bar and y bar. It is obviously clear that the channel section is symmetry about the x-axis. Due to symmetry, the y bar can be calculated. Therefore, y bar is equal to total dimension, that is the largest dimension is 640, 600 plus 20 plus 20, that is capital H, 640 by 2. So that is the 320. For the x bar, it is required to calculate the using the analytical method. Therefore, the parts have been taken, one, second part and third part. So there are three parts have been assumed: the bottom flange, web, top flange. The bottom flange and the top flange having same x distances. Here it is like that, it will pass similarly. Therefore, this is the 500 by 2, that is 250. Whereas the web, the line will not pass through the same point from the flanges, hence this would be vary. Therefore, this would be 10 by 2, that is 5. Being those values, x1 is not equal to x2, and your x bar will not is also came out as 193.46. By producing the ax and divided by the area and summation, you will get the x bar as 193.46 mm, which is not equal to the x1, x2 and x3. Hence, we need to use the parallel axis theorem to find the moment of inertia over the y axis. So for determination of momentum of inertia of the x-axis, employ the hollow rectangle method, ph cube by 12 minus small h cube by 12. So it came out as ixx equal to 2102 into 10 to the 4 of 6, or you can say 2102 567 mm to the power of 4. Determination of Iyy. For that, we require the values of d1, d2, d3. They can be obtained by using the your axes of the parallel things. Let us say these are the two flanges, and the total centroid we are calculated, that is 193.46 193.46, which is passing through the somewhere here, 193.46. But as far as your uh, flanges centroid is 500 by 2, that is 200, 250, therefore that is the 250. So this is the D1 and D3, that will be 56.54 and like this. Therefore D1 is equal to D3, that is equal to 193.46 minus 250, that is the 56.54. So this is the distance. And whereas for the web case, if we see, we will take the web also, then this would be the web area. If it is might be taken as a web. Now this is also going through the its 10 by 2 distance, that is 5 mm is the its centroidal axis. So now this is the distance of D2. This is the distance of D2. Therefore D2 is also be calculated in the similar manner. 193.46 minus 5, you will get the 188.46 here. So this distance is D2. The same procedure has been shown in the figure. So this is how it is came like that. So this is the original x bar distance. 193.46 is your original x bar distance. So individual distances are minused from the total x bar to get the d value. So therefore 56.54 and 56.54. For the web portion, only 5 is there, and so 5 has been deducted, so you will get the 188.46. After knowing those values, then use the parallel axis theorem formula. Iyy is equal to sigma Iyc plus a times of the distance square of the parallel axes. Then substitute the d values and area values, and for the Iyc we need to take the b cube h, because it would be, being it is like this and your axis is cutting like this, your axis is going to like this, hence b is to be get the cube, therefore b cube h by 12. And the same formula is also good for the remaining flanges and webs. Then substitute the values and add the same thing to the AD square term. After summation, you will get the Iy value. And in this particular question, they are asked about the Izz. For Izz, which is perpendicular to the given plane, the Izz plane will be the perpendicular. So if I say that this is xy plane, this is the xy plane, the Izz will be somewhere perpendicular to the its axis, somewhere like this. Therefore this is the zz axis, which is perpendicular to the xy plane. Zz axis, zz axis is perpendicular to the xy plane, hence use the perpendicular axis theorem. So it will gives you Izz equal to Ixx from plus Iyy. Therefore, Izz has been resulted to 2796421,753.6 mm to the power of 4. So this is the procedure for the to find the moment of inertia about the z axis. Now take the another section, that is z section. Suggest the procedure how to determine the moment of inertia of z section with the following data. If you see that by compare the channel section and z section, both have the top length and bottom length, and they are also there. Now for the channel section, let us say, so if this is the channel, these are the channel section components, let us assume that these are the channel section components, let us say, and for the z section, this part of the top flange is here, and for the web it is somewhere here, it is somewhere here, and whereas the bottom flange is like this. If understood the both the sections, if you draw an axis for the both the sections, simply see the areas. Area here is equal to area here. Area at the bottom is equal to area here. Even though their orientation is different, but area about the axis is same. Area orientation is might be different, but their area is same about symmetry. So that means the flange areas of the top and bottom, their orientation is different, but about the symmetry axis, the areas are same. Here what is the area is equal to here also. The area here is also equal to here. Hence, if we forget the orientation, the Z section will behave like a channel section for the calculation procedure. That means for the Ixx, we can employ the parallel axis theorem, whereas for the Iyy, we can for the Ixx you can also use the bh cube by 12 minus small bh cube by 12 procedure, and for the Iyy case we have to employ the parallel axis theorem. So that means if the same is there, therefore Ix of the channel section is equal to Iz of the channel section of the Z section. Ixz. That means the moment of inertia about the x-axis for both the channel section and z section will be the same. So it can be simply written like this. If to understood better, I of Ixc is equal to Ixz. So this is what I want to say, that the moment of inertia of the channel section about the x-axis is equal to moment of inertia of the z section about the x-axis subjected to the dimensions of the top flange and bottom flange for the both are the same. This is one of the conclusion. By inspection I got the idea. So hence the similar procedure can be adopted for the jet section also. So by inspection it is understood that there are two portions of the hollow portions. So one at this point, one at this point, and second at this point. So there are two hollow portions. The same thing can be uh, try to uh, get the symmetrical about the both the areas. One is up and another one is down. Hence they balance each other. They will form a hollow rectangle method. Hence that can be obtained to calculate the moment of inertia. So in that case, you can also use this equation, and for this, for the Iyy sigma Iyc plus a into x bar minus x square. So use the same and solve the moment of inertia of the centroidal z section with the following top flange and bottom flange. So apply the same methodology as we got the centroid calculation procedure to get the summation of all the things by analytical method. For the bottom flange, it would be 490 plus, from this point it is 490 plus 500 by 2. So this is entirely a 500 distance from this point to this point, it is 500, therefore 500 by 2. So this is the distance, which is 740. So this is the 740 distance. So how it is given? 490 plus, this is the 490 plus 500 by 2. And similarly for the web portion, this is the 490 and 10 by 2. So you will got up to this point, right? 495. So that is the axis will be there. And similarly for the top flange, here it would be the 500 by 2. Therefore it is only up to here 250. So this would be the 250. So with that we are understood that there are three axes are there. The first one is here, the first axis is here, and the second axis, you can say the second axis is here at 495. This is the second axis, and the third axis at the here at 250. Therefore all are at different locations. So hence we require the parallel axis procedure for the IY. So locate all those values and employ the Ixx and Iyy corresponding formula to obtain the Ixx. So bh cube by 12 and minus small bh cube by 12. Substitute the values to get the values. Determination of Iyy, then d1, d2, d3. Now substitute all those values. So those distances of d1 and d2, the distances of the centroid minus individual centroid. Therefore 250 minus 495, you got the 245 as the d1. According for the d2, the same axis will be coincidence in the web. Therefore you are getting 0 value for the d2. For the d3, this 740 minus 495, you are getting the 245. So substitute those values in the parallel axis theorem, IYC and AD square procedure. Then after summation, you will get the all the values. of the Iy values. Therefore, the Iyy is equal to 161,721,6666.6 mm to the power of 4. So with this, we are concluding that we are understood in this session how to calculate the moment of inertia and least radius of gyration for the T sections, channel section, Z section. Note down that we are calculated symmetrical sections only of these sections. So I request you please have practice all these calculations by changing the values at your home. Thank you.